This video will introduce concepts related to the connectiveness of a graph. It's a certain property that we need to talk about. And we'll begin by looking at a path, what a path is. So a path from a vertex A to a vertex B is a sequence of edges that start at the vertex A you're talking about and end at vertex B. So let me give the example of the bridges of Königsberg that we've seen multiple times here. And so let's say I wanted to have a path from A to B. I could use just this single edge, and that would be a path from A to B. On the other hand, if I use this sequence of those two edges, that would also be a path from A to B. If I instead used these edges here, again, that would be a path from A to B. And you can even get particularly crazy here. You can do something like the following. And go all the way around and then come back. As long as the edges have you start at the node you're talking about and end at the final node you're talking about, that would be a path from vertex A to vertex B. On the other hand, a circuit, this is a path that ends at the same vertex it started at. So if I want to go from A, go around a bunch, and then get back to A, that would be a circuit rather than just a path. Finally, a simple path here. This is a path where no edge is used more than once. So basically you don't want to cross over an edge you previously used again if you want it to be considered a simple path. And again, the reason why we have these slightly different definitions is that some theorems are only going to hold for simple paths and some theorems would hold for any path. So that's why we want to be clear on the difference here. Once we know what paths are, we can talk about a connected graph. A connected graph is when you can start at any vertex and reach any other vertex by a path. So the graph up here, the bridges of Königsberg, no matter where you start, A, B, C, or D, and no matter where you want to end up, A, B, C, or D, there's a path that will take you there. And so that means that is a connected graph. If I were to draw a similar one, but not quite the same here, and you see how C is all alone, nothing you get to see, that would be a non-connected or disconnected graph because you cannot get from A to C, for example. So connected graphs are going to be the baseline, and the idea is even if you have a graph that's not connected, you could just restrict yourself and just look at the part that is connected and separate other parts away from that, and you could just analyze the problem one piece at a time. So really, our default is going to be a connected graph. Now let's suppose we have a connected graph. Then they have this idea of a cut edge. So let me do another example of a graph over here. Let's do an A, B, C, and a D. And let's get some edges here. So right now, this is a connected graph. You can get from anywhere to anywhere else by a path. However, if you were to cross out this edge right here, then your graph would change. And you could no longer get from A to C or A to D or C to A, C to B, all those different combinations. It's no longer connected. So a cut edge, this is an edge that when removed makes the graph no longer connected. So that right there is what a cut edge is. That one I crossed out is an example of a cut edge. On the other hand, if you were to look up here at the bridges of Konigsberg, if you were to remove any single edge, it would still be fully connected, right? There's no single bridge that is completely important for that city. Any one bridge gone would still be fine. You could still get from anywhere to anywhere else. And since that was an example of bridges in a city, if you can imagine, say wartime back then, and let's say the people invading this city were trying to find a way to cause problems there, if there was a cut edge bridge, that single bridge that if you remove it would cause a problem, then they could put explosives on it, take it out, and there you go. Then you'd have a problem here. On this case, if they took out one of the bridges, it would not be great, but they would still have options to get to anywhere they needed to in the city. So that's just a random example where, real world case where you'd actually care about a cut edge. A cut vertex is very similar in that this is a vertex that when removed makes the graph no longer connected. Now remember that when you're going to remove a vertex from a graph, you need to remove all edges associated with that, not just the vertex itself. You don't have lines going off by themselves here. And let's do an example of this here. Let's say we have A, B, and C. All right, simple thing here. If I were to take away B and get rid of all the edges that are connected to B, then my resulting graph would have A and C completely separate, and it would be no longer connected. So that would be a cut vertex. Now once we have the idea of a cut edge and a cut vertex, we can talk about this idea of edge connectivity and vertex connectivity. And these symbols, right, this is Kappa, so you may or may not be familiar with that. That is the symbol, Greek letter Kappa. And this one is Lambda. And so the idea is, in the cases of the bridges of Konigsberg, there was no edge that if you removed it would cause it to be disconnected. However, if you were to remove all three of those edges, if you remove all three of them, then D would be disconnected from A, B, and C, and it would break it so it's no longer a connected graph. So the idea for edge connectivity is, this is the minimum number of edges that can be removed to make the graph disconnected. And similarly, the vertex connectivity is going to be the minimum number of vertices that can be removed to make the graph disconnected. And so that gives us the example of the definitions of kappa and lambda. And then we have this nice little theorem here that tells us that for any given graph, kappa is always going to be less than or equal to lambda, and lambda is always going to be less than or equal to the minimum degree of any vertex here. And so let's just give an example here where one of these, some of these may be equal to each other. Let's say I take K4, the complete graph on 4 vertices. Let's calculate things here. So if I want to make this graph disconnected, removing one edge is not going to be enough. It's still connected. Removing a second edge, it's still not going to work no matter which two you pick. But if you remove 3 edges here, if you remove 3 edges, it will no longer be connected. So for this graph, we would have kappa to be 3. On the other hand, if I want to remove vertexes, if I remove one vertex, let's say I remove, let's use this color here, if I remove this vertex and all the edges along with it, the other 3 are still connected. In fact, the other three are going to be a K3 graph. And if you remove a second one, still going to be the case. Only when you remove 3 do you have a single point there. And so for this one, my lambda of K4 is 3. And if you look at the graph here, the minimum of all the degrees is also 3. In fact, all the degrees are 3 in that case. So this is an example where all the numbers are equal. It's definitely not always the case. Let's do one that's similar to the bridges of Konigsberg, but with only a single edge in any case here. So if I want to disconnect things here, and I want to do it by edges, well, let's see here. If I were to cut out those 2 edges right there, I'm going to call this graph G. If I cut out those 2 edges, the A would be disconnected from B, C, and D, so therefore kappa of this graph would be 2. No single edge would work. Then if I want to remove a vertex here, well, let's see here. If I remove A, not going to be work. B, no. C, no. D, no. But if I remove D and B, then there's no longer any connection between A and C. So in this case, my lambda is 2, and my minimum degree is also 2. I promise you it's not always going to have all 3 of them equal. But what I would like you to do is I'd like you to practice, say on the homework, looking at different graphs and playing around with them, trying to calculate these things. On the other hand, I could ask you a question like, draw a graph that has different values for these 3 things here. So just play around with them, look at the cases of the wheels and the cycles and all the other ones there, and see if you can come up with cool examples here. But regardless, these are the concepts that we need for connectiveness.